Hey, hello there, welcome to CS School channel. In this video we are going to look at binary search problem. This problem is not asked in lot of different interviews, but you will see lot of problem based on this problem. So this is kind of a base problem on which you will able to solve lot of other problems. As usual, the link of this problem is in the description of this video, so do check it out and try to solve it on your own. If you can't solve it, come back to this video. So now let's look at the problem statement which is given on the screen. Given an array of integers num which is sorted in ascending order and integer target, write a function to search target in nums. If the target exists, then return its index, otherwise return -1. Okay, and you need to write an algorithm which runs in O of log n runtime complexity. Okay, so basically you need to find a number in the array. Okay, so here are some of the sample inputs and outputs. The first input is an array nums with this element. Okay, and you need to search 9 in this array. Okay, so 9 exists at 0, first, second, third, fourth index, right? So that's what we have written in the output, the index of the number 9. Okay, similarly there is this same array and we need to find the number 2. As 2 doesn't exist in the array, we are returning -1. Okay, so hope we are clear with the problem and the sample inputs and outputs. Now the first approach which comes to our mind is a linear search approach. In this approach we will take one variable called as I. This variable will iterate over all the array. In each of the iteration we will compare the current element with the target. If the two are matching, we will return the index I, otherwise we will move to the next element. Okay, so initially I will be -1. We will compare whether it is matching with the target. Currently it's not matching, we will move I to the next index. Okay, so now I is here. Okay, we will compare 0 with 9. Are they matching? No, right? Then move I here. Okay, now compare 3 and 9. Are they matching? No, right? Then move to the next index. Compare 5 and 9, not matching. Go to the next index. 9, compare 9 and 9. Are they matching? Yes, right? And what is the value of I now? 0, 1, 2, 3, 4, right? So I is equal to 4. Return the value of I and we are done with this algorithm. Cool. So this is called as linear search. Okay, what's the time complexity of this solution? As we are running one for loop over the entire array and at max we can process n number of elements, right? The time complexity becomes O of n. Okay, and what's the space complexity? As we are not using any extra space, the space complexity becomes O of 1, right? So hope we are clear with the linear search approach. Now let's look at how we can modify this approach to do a binary search. So now let's look at the binary search approach. In the problem, if you are given some attention, you will see that we have given a condition. The condition is that the array will be always assorted in ascending order. Okay, and that's a very important condition to apply binary search. Okay, binary search can be applied on sorted arrays only. Now how will we go ahead with the binary search? Okay, so I have taken two variables, start and end. Start indicates the starting index of the array, which is 0, and end indicates the ending index of the array, which is 5. Now what we need to do, we need to find the middle of this array. So how can we find middle of this array? We can do something like this. Mid is equal to start plus end divided by 2. Okay, so start is 0, end is 5, we divide it by 2, we get something like 2.5. okay, so we need to convert this division to integer so that we get 2. Okay, now we need to see which element exists at the second index. Okay, so the element which exists at second index is 0, 1, 2, this element, right? 3. Okay, now our target is 9, right? So this is our target. We compare 3 with 9. 3 equal to 9? No, right? 3 is not equal to 9. Is 3 less than 9? Yes, 3 is less than 9, right? Now as we know, the array is sorted. In which part of the array do you think 9 will exist? 9 will exist after 3 only, right? It won't exist before 3 because array is sorted. 9 will exist only after 3, right? So what we need to do, we need to discard this half of the array and we need to start searching 9 in this half of the array. Okay, in this case what we will do, we will move start to the mid plus 1. Okay, start will move to whatever the mid was plus 1. Okay, so start will now go to 3. End will stay as it is because end is again in this half of the array only, right? And we need to do the calculation again, so we need to calculate mid again. So let me just calculate the mid. Now start is 3, end is 5, we divide it by 2, so 5 plus 3 is 8, divided by 2 we get 4.5, and we need to take integer form of that, which is 4. Okay, so now our mid is 4, so 0 1 2 3 4. Okay, we have reached here. Now we compare the element at mid with the target. Are they equal? Yes, they are equal, so we are done with this problem. Okay, so this is how binary search works. Okay, let's just take another example to get more clarity about it. Now let's just say our target is -1. In the last problem our target was 9. Now we have moved that target to -1. Okay, so how will binary search work in this case? The starting condition will be similar. Start will start with 0 and will have value of 5. We need to find mid. Start plus end divided by 2, which is start is 0, end is 5, divided by 2, we get 2.5, which is equal to 2. Okay, now we need to the mid will point to this element. Okay, then we compare 3 with -1. Well, 3 is actually greater than -1, right? So in which part of the array do you think -1 will exist? It will exist in this part of the array, right? It cannot exist in this part, only in this part it will exist, right? So we discard this part of the array. How we do that? We actually move end to the mid -1. Okay, in previous case we have moved start to mid plus 1. Now we will move end to mid -1 because start is in the first half of the array. So we will change end to 2 minus 1, which is equal to 1. Okay, and then we will find out mid again. So start is 0, end is 1, divided by 2 we get 0.5, which is equal to 0. Okay, so our mid is now at this position. Okay, again we compare -1 with this target. Well, it is matching, so we are returning the value of mid, which is our index. So hope you are clear with this approach as well. Okay, so now let's look at what happens when the element doesn't exist in the array. So now our target is to the element which doesn't exist in this array. Okay, now we will start with start is equal to 0, end is equal to 5. We will calculate mid, which is 0 plus 5 divided by 2, which is equal to 2. Okay, then we will check the element at mid. Is it matching with target? No, it's not matching with target. Is it greater than the target? Yes, it is greater than target, right? 3 is greater than 2, right? So the element will exist in this half of the array, right? Because 3 is greater than 2, right? Now we will move end to the mid -1. So end will become 1. Now let's calculate mid again. So now the mid becomes 0 plus 1 divided by 2. So 0 plus 1 divided by 2, which gives us 0.5, which is equal to 0, right? So we are now checking this element. Okay, we compare -1 with 2. Well, they are not matching, right? 2 is actually greater than -1, right? So in this case, what we will do, we will discard this half of the array and we will move our start to mid plus 1. Okay, so we have done start is equal to mid plus 1, so 0 plus 1, which gives us 1. Okay, now both start and end are pointing to one index only, which is this 1. Okay, Then we again calculate the mid. So our mid becomes 1 plus 1 divided by 2, which is equal to 2 divided by 2, which is 1. Okay, so start, end and mid are all pointing to one element. Okay, so this element. So compare 0 with 2. Are they equal? No, right? 0 is actually lesser than 2. In this case, what we need to do, if an element at the array is lesser than the target, we need to increase start, right? We need to search in the next half, right? Then we will increase start with mid plus 1, which gives us 1 plus 1, 2. Okay, so now our start is 2, end is 1. So can there be a condition where start is greater than end? No, right? So we have reached to the end of our search and we haven't found the element. Okay, in this case we will return -1. Okay, so hope you are clear with the case where the element doesn't exist in the array. Okay, so on a broader level, 3 conditions exist in binary search. If array of mid is equal to target, in this case return mid. Okay, then the second condition is if array of mid is lesser than the target, then in this case basically this condition, if target was 9, mid was 3, then array of mid is lesser than target, right? In this case what we need to do, we need to move start to mid plus 1 because we need to search in this part of the array. So in this case what we need to do, start is equal to mid plus 1, and we need to check another condition, if array of mid is greater than the target. So basically we have reached a condition where 3, if our target would have been -2 and we have been at 3, then we need to move in this part of the array, right? So we need to do end is equal to mid minus 1. Okay, so these are the 3 conditions and we need to run a while loop whose starting condition is start is greater than equal to end, right? Because start cannot be greater than equal to end, right? Okay, so hope you are clear with this binary search approach. Now let's look at the C++ implementation of this. So one last thing to cover before we move on to this implementation is the time complexity and space complexity. So what is the time complexity of this solution? Well, in each of the iteration we are actually discarding the half of the array. Okay, and there is actually a very long proof which says that if you are discarding half of your array in each of the iterations, the time complexity becomes O of log n. Okay, so that's the time complexity because we are discarding half of the array every time in this algorithm. Okay, and what's the space complexity? As we are not using any extra space, the space complexity becomes O of 1. So here is the C++ function that we need to write for binary search. It accepts a vector of integers as an input and a target, and it expects the integer with the index as an output. Okay, so we have taken start and end. Okay, and then we have run a while loop with the condition that start is lesser than or equal to end. We have calculated mid by this formula, start plus end minus start divided by 2. Basically it adds the half of end minus start in the start, which is kind of similar to what we have done. Okay, it just avoids overflow because if you do start plus end, it can be a possibility that it will overflow the maximum limit of integer in C++. Okay, so to avoid that we have used this formula. Okay, then we have checked if nums of mid is equal to target. If that's the case, we are returning the mid. Okay, then we are checking if nums of mid is lesser than target. The first case, in this case we are discarding the first half and we are moving start to mid plus 1, and in other case we are moving end to mid minus 1. If we are not able to return the mid in this entire while loop, in this case that means we are not able to find the element, and that case we are returning -1. Okay, so hope you are clear with this C++ function implementation. For running this code, I have written a main function which has a vector of integer nums defined and a target defined, and I have called this function and I have printed the result using cout function. Now let's run this code. So we get 4 as the output, which is index of 0, 1, 2, 3, 4, the index of 9, right? So we have gotten the correct output. So hope you are clear with the problem and its solution. If you have any doubt, please ask me in the comment section. I'll be more than happy to help you. We'll be making more such videos in the future, so stay tuned for further updates and do subscribe to our channel. That keeps us motivated.